So the purpose of this lab is to predict the behavior of a circuit containing resistors in series and in parallel, measure the conventional current and potential differences in circuits, and also analyze behavior of ohmic resistors and capacitors. So the physical principle used was the conservation of energy, or the loop rule, which states that the sum of all currents that enter an electric circuit junction is zero, or just saying that the sum of currents that enter a junction is equal to the sum of currents that leave the junction. And also that the sum of voltages or potential differences in electric circuit loop is zero. So when I did the prediction for the current I1 and I2 that would be measured by the two ammeters, I just used I equals V over R and found that it may equal 0.0204 amps. My predictions were correct as shown in the diagram below, and when the ammeter was inserted back, the ammeter when it was inserted backwards, which is basically just reversing the red and the blue wires, it was the same magnitude, just negative. So when I replaced one of the ammeters with a voltmeter, I found that the voltmeter carries all 3 volts of charge while the ammeter has none, and this is because no current is flowing through the ammeter. Based on the model below given to us in the lab diagram to measure each points A through H, I found that the potential differences between A and B were negative 3 volts, between B and C were 0 volts, C and D 0.959 volts, D and E 0 volts, E and F 2.041 volts, F and G 0 volts, and G and H also 0 volts. And when summed, I found that they did equal 0. My measured differences they added up to 0. And here is the graph, the finished graph based on my measurements, the potential differences. And again, as you can see, from F to H, it was 0. So when you attach the voltmeter, you alter the circuit, and the ammeter reader doesn't change because the voltmeter has infinite resistance. And when the voltmeter is replaced with the ammeter in parallel with the 100 ohm resistor, the current through the ammeter is increased. This is because the circuit now has a part in parallel, so the circuit will split between this junction, and this is due to the node rule. So the resistance calculations using delta V over I found that for the 47 ohm, with the voltmeter now replaced, is 47.95 ohms. The 100 ohms is now 102.05, and the wire and the ammeter are still 0. So for the circuit of 10 ohms using the series, I found that when the battery was initially connected to the 10 ohm bulb in the capacitor series, the light produced by the bulb shined for a few seconds and then quickly dimmed once the capacitor was fully charged. And as the charge went on and time increased, the current speed also decreased. The time in seconds for the capacitor charged was 10.3 seconds, and when it discharged, again, the light got dimmer, except this time the current moved in the opposite direction, and the time for the capacitor to discharge was 10.72 seconds. For the 20 ohm, I have the same observations. The light initially charged and then dimmed until the capacitor was fully charged, except this time the time was increased. So the time for the capacitor to charge the 20 ohm bulb was 16.49 seconds. And again, when it discharged, the current moved in the opposite direction and slowed down as time increased. And the time for the capacitor discharge for the 20 ohm bulb was 21 seconds. Here is my data and graph based to find the time-dependent voltage across a discharging capacitor. I used the stopwatch and the voltmeter to measure my volts. And then for my line, I found that the function was y equals negative 0.1726x plus 0.0495. Again, that's the equation for my trend line, and using the equation that ln times delta V over delta V naught equals negative T over RC, you find that the slope of the line is equal to negative 1 over RC, and you can use that to solve for RC. The expected value is 6 seconds, and I found that my RC value was 5.794 seconds. So if you're doing this in real life, you would find that there would be some existence causing a small drop in current measurements. compared to doing this on a computer. And if you use the real battery to charge the real capacitor with no resistor, it wouldn't be as quick, and this is because there is resistance in real life, again, in the wires, even though there is no resistor. So it may not charge just as fast as a simulation, but it would charge more than if a resistor was present. But overall, the charge may be slower than that in the measured lab. So in conclusion, we found that electrical circuits were simulated through a computational model with ideal factors. The loop rule was proved in part 1 by finding the sum of all currents of the electric junction was 0, and we demonstrated the differences between parallels and series connections. And we found that the value of time constant RC was found to be 5.794 seconds, which is relatively close to the expected value of 6. Thank you for listening.